Jupiter, our solar system's largest planet, is made almost entirely of hydrogen and helium, making it strikingly similar to our Sun. If we're only about 80 times more massive, fusion would begin in its core and Jupiter would become a star. This raises the question, what exists between the largest planets and the smallest stars? Enter brown dwarfs, bodies that never quite made it to stardom. They don't shine like stars, and they're too massive to be regular planets. But in that strange middle ground, they may offer us a rare glimpse into how stars form, how they fail, and how the universe fills in the gaps between categories we thought were clear. But there's one big catch. How do we find them? Most brown dwarfs are faint, cold, and hidden near the detection limits of even our most powerful telescopes. We need clever methods of tracking these elusive objects, which for the past 2 summers has been the focus of my research. To find these stars, I've been building K-star, a data pipeline that targets one key characteristic, motion. Brown dwarfs often move quickly across the night sky compared to other stars, and we can exploit that behavior. Now, most astronomical datasets are created from years of imaging by telescopes, which often capture images of the same region in the sky once every few months to a year. When a brown dwarf moves between those visits, it appears in different locations each time, tricking the telescope into thinking it's seeing entirely different stars, as we see right here. With some clever algorithms and filtering, we can use this behavior to track down fast-moving brown dwarfs by filtering for K stars in alignment, which in this case is 5. We're still tuning parameters, but once finalized, K star could reveal new brown dwarfs in already existing astronomical datasets. But what if the brown dwarf is so faint that it doesn't show up in any individual image at all? In that case, we borrow from a technique used to find dim, fast-moving objects like asteroids. A software package called KBMod works by shifting and stacking telescope images along different paths, as if trying to follow the motion of a faint object, and then combining them to amplify its signal. We adapted KBMod to better fit the motion of brown dwarfs, and I found promising results. With KBMod, we found that the likelihood of detection for the true motion of a brown dwarf is significantly larger than any other trajectory, indicating that KBMod can find these brown dwarfs. By developing and combining motion-based search methods, proper motion pipelines, and shift and stack techniques, we're opening up new ways to uncover brown dwarfs that had gone unnoticed in archival telescope data. By finding more brown dwarfs, we're able to better understand their origins, the origins of stars and solar systems in general, and have a better understanding of our cosmic neighborhood. Thank you.